Okay, I believe we are live. Let me just, as always, make sure and check on the YouTube that we are going strong. Patience. Una, dos, tres, and let's see. Okay. Yes, we are going live. Okay. Welcome back, everybody, to another physics lecture review. Here I have my board, making sure that works good. Okay. We are going to continue right where we left off. We last left off talking a little bit about momentum, and in this video, we are going to introduce energy. So exciting, right? Yeah, that's pretty much all we're going to do. We're going to use integration to prove the concepts of energy that we know and love. And yeah, without any further ado, let's get right into the physics. So let me hide my face, my beautiful, beautiful, beautiful face. Sorry, there's just something on my computer. Okay, okay, here we go. Let me just pull up my notes just to make sure that I have something good to look at while we do this. So we are introducing the concepts of energy. Now, up until now, and until now I mean in my class, not really in these videos because I haven't been posting very much, but up until now we had only ever used Newton's law, F equals ma, to find acceleration, or sometimes the change in potential, the change in momentum, so dp over dt, which is the same thing as just dmv over dt, which for a lot of cases is the same thing as mdv over dt, which is for a lot of cases ma. So again, we've only ever really been looking at acceleration. We have not been looking at, for example, velocity or position, right? Because they're just harder to figure out. But that is all about to change. That is all about to change. And that is going to change with integration. So let's get that going. Okay, let's understand what an integral is, because you may have seen things like this, and you probably saw it on my last video. Something that looks like this with a function, and also like that, something like that. Like this is some kind of integral, and you want to compute what this equals. Now this is weird, so let's understand what this is saying. Let's understand what this is saying. If I tell you that the derivative of, let's say, big F over dt equals f of x, little f of x, if I tell you that, then it follows that f of x equals this, right? That is the claim. So if this, then this. And so from this, you could kind of see that the integral is almost a kind of antiderivative. It basically reverses the derivative process, if you want to think of it like that. Let's understand what it's actually saying. So imagine we have some graph, right? And by graph, I mean line. Let's just put this on the coordinate axis or something. And yeah, okay, so we have this line. Let's just say it starts at the origin. And we call this f of x. Okay, yeah, that's our line. That's our function. The integral finds the area. It basically almost finds the area between 2 points. It finds this. And you could think of the entire area not as one big section of area, but rather you could think of it as the area of a lot of little rectangles, that almost follow the graph. They follow it pretty well. I'm not actually drawing this so well, but they follow it such that one corner of each rectangle is on the line. And you're basically taking the sum. Oh my god, this is so annoying that my screen keeps on deleting what I write. You're basically taking the sum of the areas of all of these little rectangles who have, let's say, some length, delta t. And so when we say the integral, let's say this is a and this is b, x equals b and x equals a. Okay, let's say that. So when we take the integral from x equals a to x equals b of f of x dt, oh, actually, you know what, yeah, it should really be t equals b, if we want to keep things consistent. So t, this is a t, this is a t, and this is a t, and yeah, up here also t. Let's just keep our variables consistent. So it's f of t of dt. When we say this, it's just another way of writing fancily in calculus terms the limit as delta t approaches 0 of the sum from I, so from almost from t equals a till t equals b, of f of t sub I. So actually, it's really I equals a and I equals b. So all the t sub i's for whatever I we're looking at, we're taking the sum of this. Sorry, I just want to make this I a little bit better. Times delta t, right? It's the area of the height times the width as delta t approaches 0, and as delta t approaches 0, these rectangles will model our function perfectly. And when delta t is 0, it's basically dt, and it gives you the perfect area for underneath the graph. That's really what the integral is telling you. And so, for examples, some examples that might be useful to know. Yeah, let's take a look at these things in a little bit more detail. Hold on, I'm just adjusting my screen and stuff. Okay. Right, so imagine I told you that the derivative with respect to time of f of t equals t, right? Imagine if I just told you that. This should tell you that big F of t, or sorry, it's the derivative, yeah, I mean not big F, let's just say F. F of t, so the derivative of f of t equals t. So f of t equals the integral of f of t dt. F of t dt plus c. And this c is called the, oh boy, I don't know why the c went there. That makes no sense. Plus c. And the c is called the constant of integration. Const of integration. And the reason why c is here is because the derivative of f of t is telling you the slope of the line, right? The problem is the slope of the line doesn't change based on if you've gone up by a constant or down by a constant. And so the original function that told you the slope of the line, you could think of integration as the reverse derivative. The function that gave you the slope could be up or down by a given constant, and you wouldn't know. So we add c as the constant of integration, right? So this is a very brief explanation of integration because I want to get to the energy stuff. But if you want to take more looks at integration in your own time, that is totally valid. It is a difficult thing to look at. So to move forward from here, we could say that f of t equals, now here's the thing, 1 over 2 t squared plus c, plus some constant. Now why is this the case? Well, we know that the derivative of f of t equals t. And so we just think, well, what original function satisfies this? Well, f of t could be 1 over 2 t squared plus some constant, because just by the power rule, we take the 2 down. We take the 2 down, and so the derivative of f with respect to time equals just straight up t. And then the c becomes a 0, so it's plus 0, and so that's our original function. So there you go, that's one example of integration. You see how it's literally just an antiderivative, and it also tells you the area. The connection between the fact that it's an antiderivative and an area is a little bit confusing to understand, but I highly encourage you to take a look at some stuff in your free time and develop that intuition. 3 Blue 1 Brown has a great video on it. Okay, moving forward. Yeah, what if I told you that, more examples, what if I told you that the derivative of f of t with respect to time equals cosine of omega t? And so again, you should realize we're trying to find a function such that the derivative is cosine omega t. The derivative of that function is cosine omega t. The derivative of f of t is cosine omega t. Well, what would that be? Well, so f of t is going to be the integral of cosine omega t dt. And you can almost think of it that we're bringing the delta t to the other side. So we have df of t equals cosine omega t times dt. And then to get rid of the dt's, we integrate. So we integrate both sides. So the derivative of f of t is just f of t. I mean, the integral of f of t is f of t. So f of t equals the integral of this, and that's exactly what we're trying to solve. So you could almost think of these as fractions, these things over here as fractions. Not quite, but almost. For our purposes, you can. And so this is going to be, well, what do you think this will be? If the derivative of f of t is cosine omega t, then what do you think f of t will be? Well, this just follows from our basic understanding of trigonometry. We know that f of t is going to be, excuse me, sorry, big important thing that we missed, plus c. We need that plus c. And so f of t is going to be 1 over omega sine omega t, right? Because the derivative of sine omega t is omega cosine of t, and then we have the 1 over omega to just cancel that out into 1, and so here we have our f of t. Perfect. Absolutely perfect. Let's continue with another example. What if I told you that the derivative of f with respect to time is sine omega t? Well, so again, let's just bring the delta t to the other side. So we'll have d of f equals sine omega t dt. And then to get rid of the dt's, we're going to do the integral of df, which is just f. That equals, sorry, f of t. That equals the integral of sine omega t dt plus c. Now, what is the integral of sine omega t? Well, it's going to be very similar to the last thing that we had with the cosine. We'll have that f of t, f of t, equals negative 1 over omega cosine of omega t plus c. Again, I cannot stress enough how important that constant is. Should we do more examples? Yeah, let's do one more example. So let's come back over here. Here we have our sine. Now let's do another one. What if I told you that df with respect to dt equals 1 over t? Yeah, 1 over t. Okay. Well, let's just skip this step over here because that's pretty simple. Well, we'll have that f of t equals the integral of 1 over t dt plus c. And this, if you think for a moment back to derivatives, you'll know that f of t must equal ln of t plus c. And this is true because the derivative of ln of t is 1 over t, right? You can almost think of this as saying, what does this say? Well, this tells you that e to the f of t equals t, and this is the same thing as saying df over dt e f of t equals the derivative of t, which is just 1. And this is the same thing as saying df over dt equals 1 over e to the f of t. And if f of t in the beginning was ln of t plus c, but for now let's just assume that c is constant. So if f in the beginning was ln of t, then we have df. In fact, it doesn't matter. We could put the c in there anyway, but the c will just go away. df over dt equals 1 over e to the ln of t. E to the ln of t is just t, because these are inverse of each other. So this equals 1 over t. And so this satisfies the thing that df over dt is 1 over t, df over dt is 1 over t, and so f of t is ln of t plus c because of integration. Beautiful. Absolutely beautiful. Look at this. Isn't that amazing? Sorry, that's my physics homework. Okay. One more concept that I think is good to know. Not I think. It is good to know. Is, let's just make sure that's a good size. No, I want it to be a little bit bigger than that, so let's zoom in a little bit more. Beautiful. Big fan. Okay. So that's all the examples. Now let's take a look at something that's slightly more important for our thing, and that is, until now we've been looking at indefinite integration. Now let's take a look at definite integration. Definite integration. Definite integration is when instead of looking at the entire function, we just take a look at a few points. So if I tell you that the derivative of f with respect to time, sorry, hold on. Let's just denote this. The derivative of big F with respect to time equals f of t, some smaller function. This tells me that the integral from f sub a, so the first f, to f sub b of df equals the integral from t sub a to t sub b, so time a, time b, of f of t dt. Now, this makes sense because, let's think about this. F of t sub a, f of t, actually no, let's finish writing this and then I'll explain it a little bit more intense. This tells me that f of t sub b minus f of t sub a equals the integral from tb to ta f of t dt. So you see that what we're really doing is we're taking t sub b and we're putting it into f, and we're putting it into the antiderivative of f, which is big F, and we're taking t sub a and we're putting it into the antiderivative of f, which is big F. And sorry, these should be reversed. Yeah, it should be t sub. Sorry, it shouldn't be t sub b. It should be t sub a, t sub b. So what we're doing when we do definite integration is we're taking f of t dt and we're turning it into its big daddy function. So that's going to be like big F, right? And then we put the we put the b inside, so f of t sub b. And then we do plus c, right? That's our plus c. And then we do it for this one, for this number, minus big F of t sub a plus c. And so the c's cancel, and so we're just left with this value. And the reason why everything that I wrote before that is correct is because this is the same thing. Like, again, we're putting we're looking at the graph. Imagine this is a graph of little f with respect to time. We're looking at these 2 points, t sub a, t sub b. And we're trying to find the area in this location. Sorry. Okay. And then what I say is this value over here, this is what I call f sub a, right? Because it's f at t sub a. And this value over here, this is what I call f sub b. And so what I could do is I could just say it's the integral of df, which is just sorry, hold on. I must have something misput in here, because this doesn't make any sense, because the integral of df is just f, but it's not f of f sub a. That doesn't make any sense. It's f of t sub a. So yeah, I'm not sure what I wrote here. These probably should be t's. Yeah, that makes more sense. T sub b, t sub a. And so you see that we just put the antiderivative of f. That's what the integral df means. So it's just going to be normal f of t sub b minus normal f of t sub a. And that's the area. That's the area under that graph if we're looking for definite integration between 2 points. Now this will be useful for us because, as we know, velocity is the area under the acceleration graph, right? And position, if this is velocity, then position is the area under the velocity graph, right? This is stuff that we know from before. And so that's why integration will be helpful, because it's the area under these graphs. So let's put some of this knowledge to the test. Sorry, this is from last time. Let's put some of this newfound knowledge to the test. And let's now take a look at Newton's laws. And for now, let's just take a look at them in one dimension. Okay? So, let's do it. Let's do it. Newton's laws. Is this a good size? No, I want it to be a little bit bigger. Yeah, okay. Newton's laws. So oh my god, I hate how my screen deletes my stuff. Okay. We have m dv over dt equals f. Now, here's the thing though, because very often we had f as a function of position, right? Not all the time. Sometimes f was a function of velocity. But very often we had f as a function of position, not as a function of time. So for example, gravity was a function of position for the force. For example, the spring was a function of position. So what we want is, if we want to do integration, we want to get dv dt in terms of position. So we want it to be like dv dx. Now how do we do that? Well, again, let's just think about dv over dt as a fraction. Okay? And because it's a fraction, we know that we can mess with stuff. Like we can mess with it. We can mess with the units. So instead of saying dv dt, we'll say dv dt equals dv dx times dx dt, right? And this makes sense because the x's would cancel and the t would come over here, and so it works. And what's good about this is that dx dt, well, that is just velocity. And dv dx, well, that's exactly what we're looking for. This is just dv dx. Like we want dv in terms of dx. Sorry, dv dx. I keep on writing dt, and I will make that mistake a lot, dv dt, because I'm just too used to writing it. So let's put that here. So instead of saying m dv dt equals f, let's say m dv dx times v equals the force. And the force is a function of x, so f of x. And that's why we wanted the x there, because we want these things to be in terms of the same idea. And so if we want to get the actual velocity instead of dv dx, if we want to get the actual velocity, what we could do is we could do some integration. So let's set that up. Instead of saying it like this, we would say m dv v, or actually, you know what, just to make this more clean, we would say m v dv, nope, dv equals f dx. Right? I just moved the x to the other side. And so now we could integrate. Now, this actually isn't true, by the way. This statement, it's only true for a moment if we integrate. If we integrate, it becomes true. But simply because of how d's work, it's not true. Because dv is an infinitesimally small amount, and this would all just evaluate to 0, basically. Unless it's being divided by also an infinitesimally small amount, which is dx, then it doesn't evaluate to basically 0. So the point is we have to integrate. Otherwise these statements are not true. So we have to quickly integrate, and let's do that. So we have, let's say from, first of all, I want to bring this a little bit down. Let's say from 2 moments. So first of all, the m is a constant, so the m could go outside. So it's going to be m. Now from v sub a to v sub b. Yeah, we want to look at it from when v is v. And this is the same thing as saying from t sub a to t sub b, where v is a function of time. But from v sub a to v sub b, of v dv equals another integral from x sub a to x sub b is going to be, and this means the x value at time a, so like x of t sub a, and this means the velocity value at time a, so it's going to be x of t sub, sorry, not x, it's going to be v of t sub a. That's just important because what we're doing really is we are taking the integral of both sides to the same values, but we're just taking a shortcut where we're saying v is a function of time in a certain way, and so we're just going to call it v sub a and v sub b. And then this is going to be x sub a to x sub b of f of x, So f of x dx, right? That's our integral situation. Now we could solve for this conveniently. Well, if there's just a v over here and a dv, well, we saw that earlier. This is the same thing as saying that v equals dv over dt. Sorry, no, it is not at all. This statement over here is the same thing as saying that, I guess, by the way, just to reiterate, we're working in one dimension here. That's why we're not dealing with vectors. But this statement over here, v dv, is the same thing as saying that dx over what is this saying? It's going to be something over dv equals v. Oh, f, the function that we're looking for. I'm not sure what f is though. Df, the function that we're looking for. But what does the function that we're looking for represent? Is it velocity? No, it's not velocity. That would just be dv over dv. Is it position? I don't know. This is stumping me. I really don't know. Because I'm always used to it being over dt. Is dv supposed to be like... Yeah, I don't know. This is very weird. Remember we had m dv over dt equals f. If we had this is acceleration. But then we move the dt to the other side. Actually, we didn't move the dt to the other side. We changed the dt into a dx. Let's finish the process, and then maybe we can make more heads or tails out of this stuff. So let's just finish the process, finish the calculations. So using our understanding of integrals, we would have m times vb minus, is it b? Yeah, it's vb squared minus va squared over 2, right? Because then the derivative of that is going to be 2vb over 2, which cancels, so that's vb, that's what we have up here. And then the derivative of this is going to be 2va over 2, those cancels, and so that's what we have over here, right? So yeah, so that's the answer for one side. That's the integral for the one side. And then the integral for the force, so this equals, oh, we just keep that as an integral. The integral from the first position to the second position of force times dx, for f dx. And so I guess this depends on the force. So here's the basic idea. This depends on the force function. Obviously, we can't solve this without knowing the force function. But what does this represent really? Yeah, it's a little fishy. I guess I'll ask the professor today at lecture, and maybe I could clear this up next time. But for now I'm not 100% sure. Okay, let's take a look at an example. Let's take a look at an example. So let's just make a line, and the example will be simply the good old ball flying up into the air with some velocity v, and some force pulling it down, some force g. Let's understand its motions. Well, we know that negative mg equals, the acceleration is in the same direction though, so hold on. Sorry, hold on, just give me a second, because there's a, I'm just trying to think about the negatives. dv over dt. The force F mg equals dv over dt. What? What did I write here? I wrote negative mg, that's the force, equals, what? No, sorry. This is the, ma equals, why did I write that it equals dv over dt in my notes? That's just not true. What? There's supposed to be an m there. Yeah. Yeah, okay, so m dv over dt. That was weird. And so the m's would cancel. But the only thing is, I don't think that we're supposed to have a negative, right? Because dv over dt is the same direction as g, right? So I think it's just positive. I guess I made a mistake in my notes, because my notes say negative, but it doesn't make any sense to me, because dv over dt is the same direction as g. And if one of them is negative, then the other one has to be negative, so they're just both going to be positive. Okay, and so if the masses cancel, we have g equals dv over dt. If we want to integrate to find velocity, we just bring the dt over to one side. dt g, or g dt equals dv. And then we could integrate from t sub a to t sub b of g dt equals another integral from v sub a to v sub b of dv. And this is going to be quite simply, how much more room do I have? No, let's move this. Let's move these guys a little bit more to the left. Let's continue. And this is going to tell me that quite simply we have, so the g could go on the outside, it's a constant, and dt from time ta to time tb is just going to be, it's just going to be g times tb minus ta, right? Because we're doing definite integration. And this equals vb minus va, right? Because of the integration. Okay, and so now what this tells me that that vb, right? Okay, so how about vb equals va minus g times tb minus ta. And so if we just think about it such that, actually no, that's fine for now. So now let's think about what vb is. So vb, the velocity at time b, is simply dz over dt, right? Well, I mean, I guess z, right? Let's just make a coordinate system where this is the z direction, I suppose. And like, I guess this is x and this is y, right? So we're looking for, it's flying up, right, in the z direction. So this derivative over here, this vb, is simply dz over dt equals v sub a minus g times t minus ta. The reason why it's just t is because we got rid of the sub b part, right? So there's no more sub b, it's just for any given moment in time, right? So you can think of this really as delta t, right? Because if I want just dz, I can't have dz sub b. So this had to be a normal t. And so again, if we just want to find out what z is, we would have an integral. Sorry, hold on. Let's just move this down a little bit so that I have room. We would have an integral from z sub a till z sub b of dz, right? We're going to integrate both sides, equals an integral from t sub a to t sub b. Hold on. Yeah, t sub a to t sub b, I think, of va minus dt, right? Because not minus dt, va times dt. Because notice we brought the dt to the other side again, and then we also have to account for this element, which is just going to be a separate integral altogether. That's how integration works. Minus another integral, and this time it's still going to be t's, t sub a, t sub b, of minus g times t minus t sub a, t minus t sub a dt. And so notice how we have a minus minus over here, by the way, because it's interesting. Sorry, hold on. Do I have a minus minus? I do have a minus minus. That's weird because in my notes I also have a minus minus. But if I have a minus minus in my notes, then I must have made a mistake here. Yes, I made a mistake. This should be plus. But that's a problem. That's problematic. Hold on. I'm messing up the minuses. Remember minus issues? Mg, if g is positive, dv dt is the same direction as g, right? So they should both be positive. And if the m's cancel, then we have g equals dv over dt. We have g times dv is going to be this. G times dt equals dv, which tells me that the integral is like this, equals that, which tells me that g times t sub b minus t sub a equals v sub b minus v sub a, which tells me that v sub b equals v sub a plus, yeah, but that doesn't make any sense. Like v sub b, if v started out going up, then v sub b has to be whatever. If v started out going up and gravity is going down, then v sub b has to be whatever it started off minus a certain amount. But the signs that I have over here say that it's going to be whatever it started at, that v sub b will equal v sub a plus g times tb minus ta, which means that something's wrong with the signs, but I can't find where anything is wrong with the signs because, quite simply, dv over dt is the acceleration, and the acceleration is negative, and g, I guess, I guess over here I'm assuming that g has inside of it the negative component. Like g as a variable has a negative inside of it. And then if g as a variable has a negative inside of it, then it will continue to have the negative inside of it over here. So this is really negative. And so when it's plus, okay, so you know what? Let's just say that g itself is a positive value, I guess. And then this is going to be minus mg, right? Like g itself is a positive value. It's the value of gravity, and it's going to be minus mg, so that all of this works out. And so then we have the minus over here, and so it works out over here. That's going to be v sub a minus g. Yeah, that's fine. Okay. Silly me. Okay, and then we have, okay, double minus, which is nice. Okay, moving on. Back to where we left off. Yeah, we have dz, the integral is going to be the integral of the other side. So this is just going to be z sub b minus z sub a. Z sub b minus z sub a equals the derivative of this between two times is going to be v sub a is a constant. V sub a doesn't change through time, right? So it's just going to be v sub a. And then dt is simply going to be times, yeah, so times t sub b minus t sub a. And then that plus, because of the double negative, plus, that's interesting, because t is not a constant. T changes through time. T sub a doesn't change through time. So that's going to be interesting. We have to figure out how that works. I guess we just keep, the g will come out. The g could come out. So it's just going to be plus g times the integral, which is going to be, hold on. What? Wait, what? This is weird. Minus that. That's the t. Plus g minus the integral of this. What is happening here? I guess what we could do is we could think of it as we're going to distribute the g. So it's going to be t sub a, t sub b, minus t sub a, t sub b, minus gt, plus ta, and then all of that times, plus g, ta, and then all of that times dt. And yeah, now we can't take, I mean the g could still come out, but we still have a problem. How do you integrate this type of situation? Okay, let's just break this down a little bit. It's going to be plus g times the integral from t sub a to t sub b of t minus t sub a times dt, right? That's what we're dealing with. The g came out, and so the negatives canceled, and so that's good. And, right, moving on. We have an issue. Is it just going to be g of t sub b minus t sub a plus minus g t sub a? Is that what it's going to be? Because that's the integral of this, and then this is the integral of this, and then that's times the g's over there. Not sure. Not sure how this works, and my notes seem a little bit uncertain as well. G times t sub b squared minus t sub a squared. Oh, that's sorry, that's my bad with just the normal t. Okay. Plus t sub g times t sub a times yes. Okay, so the integral. Okay, so this is it's gonna be broken up. Let's rewrite this over here on this side of the page. So we're gonna have z sub b minus z sub a equals, the first thing that we had was VA times T sub B minus T sub A. VA times T sub B minus T sub A. And then that's going to be plus G times, and we could sort of just get rid of these two being together and make them their own separate integrals. So plus G, and then that times the integral from TB to TA of T dt minus the integral from TB to TA of just T sub A dt. And then the T sub A will come outside. But we can think about that later, so okay. And then this is going to be, hold on, I just want to make sure my signs are correct. My signs are incorrect. Why are my signs incorrect? I don't think that my signs are incorrect. Yeah, we have V sub A dt minus Oh yeah, this should just be a normal. This should just be a normal g. Sorry, that shouldn't be there. That negative. Sorry about that. And so then this should be minus. Right. Okay. And so this is going to be z sub b minus z sub a equals. Let's do this thing first. So we have g times. This is going to be t sub b minus t sub a. So equals g. Sorry, hold on. No. It's gonna be t squared minus t sub b squared minus t sub a squared over 2. Yeah, so it's gonna be g times t sub b squared minus t sub a squared over 2, right? Because that's the integral of t. And then this is going to be, yeah, that's positive, I believe. No, that's negative. Hold on. Oh, right, yeah, sorry. This needs to be normal subtraction. Yeah, so that's negative. So this is going to be negative. So there you go. And then we have the second part, which is going to be plus, because the double negatives. Now we have a double negative. We have negative over here, and we have a negative over there. So that's going to be plus g t sub a, and then dt became t sub b minus t sub a. Right? Okay. And then we have that plus just simply v sub a times t b minus t a. Okay. 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 So this is our crazy thing. So z sub b minus z sub a is this mess. Now what's cool though is that we could say what if t sub a equals 0, and also like we're looking at the beginning of our moment, right as the ball lifts off the ground, basically, essentially. And then this means that v sub a is going to be 0 as well. We're looking at the first moment that the ball just flies off the ground, so v sub a, sorry, no, v sub a is not 0. V sub a is just v naught, like the velocity at the beginning of the entire operation, right? So what happens if this happens? Well, let's simplify it. So, and and so z sub a is going to be 0. Just, we're going to set that as the origin. Or maybe even not. Maybe we don't even need to do that. We could just, whoa, go back down, excuse me. We don't even need to do that. We just have to say z sub a equal, no. We don't have to write anything about z sub a. What I'll do is, this tells me, no, I don't want that. That looks like a greater than sign. This tells me that delta z, the change in your z direction, equals negative 1 over 2 g times, right, because it's negative 1 over 2 g, the 2 is here, times t sub a is 0, so it's just t sub b squared, and yeah, that's fine, plus this all evaluates to 0, which is convenient, extremely, because t sub a is 0, plus v naught times t sub b. And this is an equation that that I believe we all know and love. Oh, there's something that we're missing, I'm sure. Oh, no, because we're looking at delta z, sorry. So this is that. That's an equation that I'm sure we all know. This is another way of saying z sub b equals negative 1 over 2 g t sub b squared plus v naught t sub b plus z sub a, right? The starting off thing. So these are two kinematic equations that I'm sure we all know and love. Okay, I'm sorry, by the way, that I can't explain the integral up here very well. Something is a little bit off with how I'm understanding this. I don't really understand this idea that you're going with d. Like, what would this even look like? We have a function, and that's called v, and we're looking for the area under the function between, this is v sub a, and this is v sub b, for tiny increments of v. So like that. I don't know, I guess that works. Yeah, because I guess d sub v is also tiny increments of t. It's just a little bit weird. Yeah, honestly, I guess that works. Yeah, that does make sense. So yeah, that's how you understand it, I guess. It's a function v, and we're looking from v sub a to v sub b, and we're looking at tiny increments of v, dv, tiny increments of v for the. No, wouldn't dv be this? Right? Because if we think about it as a sum, as delta v approaches 0 from I equals VA to I equals VB, and we're looking at V sub I times delta V. That doesn't make any sense. I'm going to talk to my physics professor about this. Yeah, I'm going to talk to him about this, see if he can explain things to me a little bit. Anyway, moving on. Time to actually prove energy. I'm going to prove gravitational energy and not Hooke's law energy for momentum. So let's take a look at energy. Think about this. If I told you that a ball was shot, like if I told you the parameters for this, that V naught equaled like 5, tell me how high it would go, you would have to calculate what T is using the equation for velocity, which we had over here. Yeah, you would have to find out what T is when it reached its final point in order to find out how long it's flying up, and you would have had to do a whole bunch of crazy things to find its highest point. And it's annoying. That's why we invented something called energy. Energy is like a shortcut for these things, and it's pretty cool because energy does not involve time. There's no idea of time in energy. There's implied time somewhere, but you don't need to know time to use the equations of energy, which is really cool. So let's take a look at energy. Well, we had this idea proved earlier that m times vb squared minus va squared over 2 equals the equals the integral from xa to xb of f of x times dx. Now, if we consider this for gravity, f of x times dx becomes simply mg. And if we follow through with the integral, we get the idea that 1 over 2 m times vb squared minus 1 over 2 m times va squared equals mg times x sub b minus mg times x sub a. Isn't that super cool? Isn't that super, super cool? Something is very wrong. Hold on. Did I mess something up? I don't think so. Hold on. Something's wrong. In this case, I guess, yeah, there's no reason for velocity and gravity to, hold on. Yeah, they should have a negative. G should have a negative. So let's just put that negative here, and so that's why this becomes a negative and this becomes a positive, essentially. And so using this idea, we could say that let's get all the A's and all the B's on one side. So we have mg x sub a plus 1 over 2 mv sub a squared equals 1 over 2 mv sub b squared. I'm actually going to put that over here. And then that is going to be, plus mg x sub b. And really x should be z, because we're talking about like positions in the z direction. But I started off with x over here, and so I wanted to follow through with that all the way. So to rewrite this, maybe in terms of, let's rewrite it in terms of g. So mg z sub a plus 1 over 2 mv sub a squared equals mg z sub b plus 1 over 2 mv sub b squared. And what's interesting is that you see that these are two different moments in time, and yet something is being conserved, right? The sum of these two things is always equal. And so that thing that we call that's being conserved is energy. So even though this may change to this, zb to za, the sum of them doesn't change. And so we call this component the potential, energy, I'm just going to put E, and this is the kinetic, kinetic. And the reason for that is because this one has location in its idea, and so potential energy is the energy related to your location, and this one has velocity in its situation. And you actually see that kinetic energy always shows up as 1 over 2 VA squared, and if I had time, I would prove that for Hooke's law as well, for the spring as well. But you can use these to solve problems that were otherwise very difficult to solve. So for example, our ball issue, the ball issue you can solve. So imagine we want to find the max height of a ball that's been flown up. Well, V sub B, the end is going to be 0, right? We don't know what that is. And imagine we're given V sub A, like we have V sub A. They told us how far they hit it. Let's say V sub A equals V. And yeah, and we're trying to find H. So we simply say, well, oh, and H sub A equals 0. Like we're starting off at the bottom. So we say that, mg, sorry, my bad. We say that 1 over 2 mv squared equals mgh, right? And so if we're trying to solve for h, we cancel the m's, and we get that h equals v squared over 2g. And wasn't that super simple, as opposed to what we would have had to done with our kinematic equations? No, kinematic equations. It's much easier to do with energy. Anyway, that's the end of the video. I have to go to class now, but it's been a pleasure. Hope you guys enjoyed and learned. I will find out more about this integration issue, and we'll start off with that in the next video, I guess. So, see you. I'm gonna